Welcome to Chapter 12, Sound. We're talking about Section 2, Part A, which is sound intensity, and we're just going to highlight one thing from Section 3, actually, on page 430, which is beats. So what we're going to do is we are going to calculate the intensity of a sound wave. We're going to connect the ideas of intensity, decibel level, and perceived loudness. And we're going to relate frequency difference between two waves and the number of beats that we hear per second. So I need you guys to recall that waves carry energy, not matter. And so one of the ways that we measure that with sound is something called the sound intensity. And the intensity of a wave is the rate of energy carried by the wave through an area. So if you remember, the rate of energy is a unit we talked about before in Chapter 5, and it's called power. Okay. So then, because power is the rate of energy transfer, we actually define intensity then as the power transferred by the wave in a given area. So let's look at an equation. What that ends up being is we end up having intensity equal to the power, and then remember, power goes out as a spherical wave, right? So if our source of the wave is here, okay, it's going to go out in this direction, and also towards us and behind. Okay, so it goes in all directions. So anytime you have a sphere, okay, a sphere, we end up with an area that is this. So that's how we get this 4 pi r squared. So intensity, and it doesn't have an official letter, but to make it easier for us in our class, we're just going to use the capital letter I for right now. And so intensity is equal to 4 pi times the distance from the source squared. So what that means is intensity is inversely proportional to the distance and directly proportional to the power. So let's take a look at calculating this, for example. So at a maximum level of loudness, meaning they're playing as loud as they can, the power output of a 75-piece orchestra radiated as sound is 70 watts. Remember, watt is the unit of power. What is the intensity of these sound waves then to a listener who's sitting 25 meters from the orchestra? So we have our equation that we learned where intensity equals power divided by 4 pi r squared, and don't forget that's all under that divided sign. Then, as I just said, the power we can identify from the watts, 70 watts. And then we have the radius being 25 meters. And so if we plug that into our equation now, we get intensity equals 70.0 watts divided by 4 pi times 25 squared. And that comes out to 0.008. And intensity doesn't have a unit of its own, but it's watts divided by meters squared, so that is what we use for our unit, watt per meter squared. So as we look about intensity, what does it have to do with our hearing? Well, there's this handy table in your textbook, okay, so you can find it in your text in Chapter 12, Section 2. And it helps us understand the relationship between intensity and frequency, which you can see on the bottom here, and what that has to do with our hearing. So in just normal everyday speech, you can see that it's highlighted as this region. So when we're talking, this is the level of sound. We talk between roughly 100 and about maybe 7,000 hertz, okay? And then our intensity is only between maybe 10 to the negative 9th here in the middle and almost 1.1 times 10 to the negative 4th. So this is just, when you're listening to me and my voice is talking somewhere in here, music takes this expanded region. And then this whole line around the outside, this is called the threshold of hearing. Okay? This bottom line is the threshold of hearing, and this top line is the threshold of pain. So up here, the intensity gets so big, okay? And you notice it changes a little bit with the frequency, but sounds hurt at this level, okay? And at this level on this side, okay, we can't really hear them. Anything below this or in this region, we can't hear at all, okay? So when we take that and it's had that combination of frequency on one column and intensity on the other, we can combine that into something we call relative intensity. And the decibel is a unit used to describe the loudness of a sound, and it's connected both to intensity and our ability to hear a certain sound wave. So the decibel scale is a logarithmic scale, which means that an increase of 10 decibel is really 10 times as strong. So let's say we had something that started at 1 decibel, and we use a lowercase d and a capital B when we talk about decibel. So let's just highlight that up here. Remember that, decibel. So if something is 1 decibel and it increases to 10 decibels, okay, then what's happened is it's 10 times as strong. Okay, so we've multiplied it by 10. If we increase that again by 10 to 20, now we're at 20 decibels. Okay, we've increased that again by 10 times. So what that means is going from 1 to 20 decibels is a 100 times increase in the relative intensity of the sound. So the last thing we're talking about today then is beats. And this is to help us answer the question of what happens if we have two sound waves of different frequencies, and we mean a constant frequency, like when we talk, our voice goes up, our voice goes down, we're changing our frequencies all the time. So what happens if you have two waves that have a constant frequency and overlap, okay, meaning they're going to interfere? Okay, so will it be constructive or destructive interference? It's easiest to understand this if we look at a picture. So here are two waves, and if you look at them, they don't quite have the same wavelength, although they look quite close, right? So if you look at where things line up, okay, and here the CI stands for constructive interference, and DI stands for destructive interference. So if you look here, you've got the peak of this wave here, and then right above it, we've got a peak of that wave. So that means we have this constructive interference. But as the wave keeps waving along, we find later that here we have a trough of our wave at the same time that we get a peak. Okay, so now we have destructive interference. And this pattern repeats. So you get constructive, and then you get destructive, and so on. So what happens then is we get this nice green pattern down here, so that here the waves are adding up because it's complete constructive interference, and here the waves are completely off, and so you get destructive interference. And so what they've done here in this picture is they show the red and the blue overlapping, so you can see right here it's a destructive, and you can see here it's destructive. And you can see here the waves almost match up perfectly, and so it becomes constructive. And so you get this effect where the amplitude goes up and down and up and down. And what this sounds like to us is a sound called beats. And you're going to have to check out a separate YouTube video to hear that. So make sure you do check that out, and I will have the links posted for you. But what this amplitude, remember amplitude refers to energy, so we hear this as loudness. So it gets louder and quieter and louder and quieter and louder and quieter. Okay, even though there's these two waves happening. So here are the YouTube pages. You can pause it and write them down or check them out in the links below. And so I just want to give you the book definition here of beats. So it's the periodic variation, which means changing, in the amplitude of a wave. That is the superposition of two waves of slightly different frequencies. It can be harder to hear if they're greatly different frequencies. And that's because we can calculate the number of beats per second by finding the difference between the two frequencies. So say in our last example, one of our waves was at 512 hertz, and maybe the other wave was at 508 hertz. Then we're just going to combine those two. Okay, and when we combine them, all we have to do is take the difference. So 512 minus 508 is 4. Okay, and this is the number of beats per second we'll find. So we'll get 4 beats per second. Okay, you do need to remember this, but this isn't a specific equation, so you won't be given it on a test, but just got to remember to subtract them. Okay, and this is why if we have, why we can hear it when it's only slightly different frequencies, because you can imagine if we had 512 hertz, if we had 512 and we had one that was 300, right, then the difference is 212. It's going to be very difficult for our ears to detect 212 beats per second, even though that would be the number of beats that are happening. Okay, you guys might have several questions about this, I imagine, and we'll be doing some demos in classes to help you understand this just a little bit better. So I'll see you in class.